Thank you, everyone. Thank you for joining in today. So today we have Dr. Lalit, who will be talking about his PSIM paper, design of a 100-watt radiation-tolerant power factor correction buck AC-DC converter. We thank Dr. Lalit for giving this presentation. Please go ahead, Dr. Lalit. Please go ahead.
Okay. Maybe I'll first minimize this. Yes, so that the full screen is available. Okay, first of all, thank you, Professor Janmejaya Chennegowda, for this opportunity to present my work to the power electronics community. And now that everyone is attending talks and conferences online, every event is international. So that's something unique as well. So I thank all the audience for making time to attend this presentation. So let's start. As Janmay mentioned, this is on a paper that we already presented at the PSIM conference this year, PSIM 2020, on the design of a 100-watt radiation-tolerant power factor correction buck converter. This is an AC-DC converter. Just to check, is everyone able to hear me, Janmay?
Yes, sir. Yes.
Okay, I'll continue. As I said, this is an AC-DC converter topology. And to introduce myself, I am Lalit Patnaik. I'm currently a fellow at CERN in Geneva, that is in Switzerland. And my current role is that of a power electronics engineer designing radiation-tolerant power supplies for use in the Large Hadron Collider tunnel. So these are for controls crates. So you can think of them as switch mode power supply, like an SMP is for a computer, something in that size or so. But the computer is installed 100 meters underground. Just to introduce the Large Hadron Collider, or the LHC, as many of you might be aware of, is this 27-kilometer long circular tunnel underground. And this is straddling the Franco-Swiss border near Geneva. So what you can, okay, maybe I'll just start the pointer. What you can see here is Lake Geneva, and these are the Swiss Alps. And so this tunnel, as I said, 27 kilometers long, is underground, and this is where you accelerate the protons to very high energy and then collide them against one another to investigate into the fundamental constituents of matter. So this is a physics experiment, but what is interesting is that CERN has more engineers as employees than physicists, because to be able to carry out this experiment, there is a lot of high-end engineering required, spanning different fields of engineering. So here I am as a power electronics engineer helping high-energy physicists do their experiments. And this LHC is now foreseeing an upgrade. This upgrade is called the High Luminosity LHC project, which will happen starting from 2025. And in this upgrade, the main objective is to increase the number of proton-proton collisions 10 times. And this will result in an increase in the discovery potential of the LHC, because essentially you are increasing how probable it is to produce rare processes or rare events not seen before. If you want a more detailed explanation of what is the High Luminosity LHC project, there is this very nice video about 30 minutes long in YouTube, where you can see that if you're interested. Moving on, coming to the distributed IoT project, or the DIOT, within the High Luminosity LHC mega project, the DIOT project is like a sub-project, or what we call as a work package. And this is for developing high reliability, high availability custom electronics that can be used by different CERN user groups. And what you see in this picture here is the tiered or the layered architecture of the control system hardware for the LHC. So the lowermost layer is what is called the distributed IO tier. This is the layer that is closest to the machine, to all the actuators and sensors that are directly in the LHC machine. And above this layer are all the higher layers of control, with the topmost layer being, of course, accessible to the physicists. That would be, of course, a very high level of abstraction. But we are talking of the lowest layer, lowest level of hardware close to the machine. And we are talking of installing these DIOT crates, which are essentially 19-inch racks, installed in this layer. And some of these you can see are with this green symbol, which is radiation free, kept in areas that are not exposed to ionizing radiation, whereas the others have this radiation symbol. So these crates are exposed to ionizing radiation because of the proton beams and the collisions happening. If you want more information on the DIOT project, there is this project wiki on the open hardware repository, which will tell you more about it. In this presentation, we are focusing on those DIOT crates which are installed in radiation exposed areas. This is a picture of the physical crate, which is still undergoing design and development. Essentially, as I said before, it's like a computer. It has a motherboard or a system board and a number of different peripheral boards, in this case up to 8 or 9. And then you have these two slots here, which are power supplies. These the crate is about 3U high, and this is the standard Euro crate form factor. What you see here is because we use these crates in very safety critical applications, we have to have dual redundancy for the power supply. So it's not just one power supply, but two power supplies feeding the crate. So in case there is a failure with one of the power supplies, the other is still supplying the crate. The crate just cannot power down because of its safety critical nature. And now that you have two of them, there is also the option to do power sharing if that is required, in terms of running the power supplies at lower stress in terms of temperatures. But that is an option available when you have this dual redundancy. And these power supplies, as I said, would be similar to many compact PCI serial power supplies. This is one from Schroff, a company that makes these power supplies. But note that the off-the-shelf power supplies for such crates are actually the normal variant, the regular variant, which is not radiation tolerant. And what we are trying to do right now is develop a radiation tolerant version for these power supplies at about 100-watt power level. So RaTOPUS is the name, and it's a loose acronym for Radiation-Tolerant Power Supply. The objective of which is to design and test a generic PSU for these DIOT crates, and these will be used under radiation environment by various CERN user groups. So we are targeting something like 200 installations, 200, but then you have dual redundancy, so up to 400 installations of this in the LHC tunnel. A key point about this radiation tolerant development is that we are using commercial off-the-shelf or COTS components. So these are just regular components, devices that are sold not as rad-hard devices. These are similar to any other products, standard products that you use in commercial applications. And the reason why we use COTS components and not use radiation hard components is that the cost of radiation hard components tends to be an order or even a couple of orders more than COTS components. So that is 10 times or 100 times costlier. And if you want to install several of these power supplies, it's just humongous cost to be buying so many radiation hard components. So that is a key aspect to keep in mind, radiation tolerance, but using COTS devices. What you see here in these two pictures are the power supply architectures. On the left-hand side for a typical power supply in this kind of an application, and on the right-hand side, the power supply architecture for our RaTOPUS power supply. First, on the left-hand side, the typical power supply. Most of you in power electronics domain might already know that you typically, if you have a 230-volt single-phase input, you have an, after the EMI filtering, you have an AC-DC stage, and then some kind of a high or 400-volt DC link generated by this AC-DC stage, followed by any number of DC-DC stages to generate the required backplane voltages required by the system. And this typically would use what is called a power factor correction boost converter. The one on the right-hand side is what we are using, where again we have the same kind of 230 volts input, but the AC-DC stage, instead of being a boost, is a buck topology, which is not standard, which we will discuss a bit about why we chose a buck topology. But because of using that, you can have a much lower, let's say 48-volt DC link, from which the DC-DC converters can tap off to produce the required voltages. And just as the DIOT project, even the RaTOPUS project is open hardware. So you find it, all the files and documentations are available on the open hardware repository. This is the wiki page link, and the repository for all the CAD and simulation files is also in the same link, available in the same link. At this point, I can take a pause if there are a few questions.
Right now, no, there is one. Yeah, Nachiket, please unmute yourself and go ahead. Nachiket.
Yeah, Dr. Lalit, are you able to hear me?
Yes, yes, please go ahead.
Yeah, so my question is the application under study, does it impose any additional constraints on the this PFC, such as maybe the load is varying at a very large rate? Any additional constraint does it impose?
Actually, I would say no. From a dynamic loading perspective, most of the dynamic loading is actually handled by, let's say, the local capacitors in the load, but also by the DC-DC. So the DC-DC stages are designed to have a much larger bandwidth, control bandwidth, so that they handle most of the dynamic loading, and hardly any is handled by the PFC stage. So in that sense, I would say it's not a very stringent requirement. If that answers.
I think that answered my question. So what you are suggesting here is the PFC loop bandwidth will be limited to ensure good current quality, and the DC-DC converter bandwidth will be large.
Exactly. Yeah. I mean, if I have a large bandwidth for the PFC, as you said, my power quality on the input side will go for a toss.
Okay, so can you put some figures in this thing? I mean, what will be the bandwidth of DC-DC converter and
it's about
PFC?
10 hertz. I have it in one of the slides that comes later, but it's about 10 hertz.
DC-DC converter, I'm asking, sir.
DC-DC. DC-DC was in the range of 8 or 10 kilohertz, if I remember correctly.
Yeah. Okay. Yeah. Thank you.
Oh, thank you, Dr. Lalit. Please go ahead.
Yeah. Okay. I'll move to the next slide. Okay, so in this presentation, as I mentioned before, we are focusing only on this PFC buck AC-DC stage and not on any of the other stuff in the RaTOPUS overall power supply. Since we are talking of power factor correction, I thought I will bring up this very nice publication by H. Endo. This is the very first publication in 1992 on buck topology for power factor correction. And this figure is right off that paper. And essentially, it shows the 3 different methods for doing rectification in single phase applications. You could just have a diode bridge and a capacitor, and many of you might be aware of that it results in very spiky currents, which is not something the utility company would like. It has very poor power quality, very large harmonics, harmonic magnitude, harmonic current magnitude. So you now have these 2 approaches if you want to, let's say, smoothen the current a bit. So the standard one is the boost topology, which has current like this, measured on the DC side, that is, after rectification. And this is what any off-the-shelf SMPS that you open up will use, probably 100% of them, if not 99, maybe. What we are talking about is this PFC buck topology, where you see a buck converter sitting here, and you have a current which is not as good as this in terms of the power quality, but you can see that it is still much better than the typical diode rectifier current. You still have a nice rounding of the current, but you tend to have this small crossover distortion, or what is called the blanking period between the current pulses. But this can still be good enough for lots of applications where the power requirement is less than 200 or 300 watts. And this is what interests us here. So why use a buck topology? Let's say you have the typical boost topology, which is 400 volt DC link. The AC-DC stage as well as the DC-DC stage must use 800 volt MOSFETs. And that is weird. Why do we need 800 volt MOSFETs, one would say? So the point is, because we are using this power supply in radiation exposed applications, you need to derate the VDS rating of the MOSFET. So if the maximum blocking voltage of the MOSFET expected in this topology is, let's say, 375 volts or so, a 400 volt MOSFET or 500 volt MOSFET is not enough. You have to use double of the required voltage. So 800 volt is the, let's say, a standard value. And that you have to do anyway for the AC-DC stage. But if the DC-DC input is 400 volts, even the DC-DC stage will have to use such high voltage rating MOSFETs. Which could be an issue because, first of all, if you have a higher voltage rating device, it tends to have a higher RDS on, and even its parasitic capacitances are larger, and all of these can become an issue. Whereas if you use a buck topology, which let's say a 48 volt DC link, of course, the AC-DC will still have to use 800 volt MOSFETs because it still has a higher voltage input. But the DC-DC stage now has a much lower voltage input, and you can make do with a couple of 100 volt MOSFETs, which have much lower RDS on than the 800 volt MOSFET. And another, if you have this low RDS on, of course, the main gain for you in the design is the efficiency improvement compared to using higher voltage rated MOSFETs. And of course, even in terms of availability of COTS MOSFET options, there seems to be not many options in the range of 300 to 450. So if, let's say, you had something like a 80-90 volt DC link and you need a 300-400 volt MOSFET, you might not have a MOSFET, COTS MOSFET, which when tested under radiation passes all the tests. So it's just a matter of probability. You want lots of options of MOSFETs in the rating that you need, so that even when these COTS MOSFET are tested under radiation, some of them do pass the radiation tests. By the way, this data that I have shown here is just from Farnell, where I just go and type power MOSFETs across different voltage ratings and see how many parts they have. But this is kind of representative. You will see the same kind of patterns in other suppliers like DigiKey and others. Still on the
there is
top.
one question, Dr. Lalit.
Yeah, sure.
There's one question by Nachiketa. The blanking period in grid current will be a function of output voltage. So if output voltage increases, blanking period will also increase,
That is
and therefore
correct.
current quality drops.
That
So
is correct.
do you have any comment on the extent to which the current quality will be acceptable?
So in fact, the choice of the DC link voltage is decided by this factor as well. I have a slide on the choice of the DC link voltage later.
Okay,
but yes, if you basically have, let's say, something like 200 volt DC link, then as you look at this AC voltage waveform, let's say 200 is somewhere here. This peak value is about 325 volts for a 230 volt RMS voltage. So if 200 is somewhere here, for all the time that this AC voltage is less than 200, the buck converter is basically not doing anything. So that is when you have this blanking period. So the higher is this DC link voltage, larger is this blanking period, as Nachiket pointed it out rightly. So yes, it is a kind of a trade-off here. And again, if you go too low on the voltage, let's say 36 volts or even lower, then there are other issues with respect to the required duty ratio at which the MOSFET operates is so low that you can have large spikes of currents and efficiency becomes very poor. So it's like a trade-off, and we arrived at a good compromise at about 48 volts.
Thank you, Doctor. Please go ahead.
Okay, so I already went through this. Yeah, power factor correction, still on the topic of why use a buck topology. An interesting thing about the buck topology is that it has inherent inrush current limiting. In a boost topology, you cannot do inrush current limiting. Whereas in a buck topology, by just soft starting the duty ratio of the MOSFET, you are able to do inrush current limiting. And in our prototype, it was below 1 amp or so. Whereas if you just pull out the data sheet of any 100, 200 watt SMPS, you will see that the inrush current is typically in the order of tens of amps. 20 amps, 30 amps are very common. And in order to, let's say, even limit it so that none of the devices are damaged because of the inrush current, you need the NTC, or negative temperature coefficient thermistor. So it offers a high resistance at the start, but once it heats up, the resistance goes really low and it doesn't affect the operation. Now, because we are using a buck topology, we can eliminate the NTC thermistor, which is a little bit of a reduction in cost and PCB real estate. But what is also good is that there is a small efficiency improvement. And this is because even though the NTC thermistor is supposed to be having low resistance during normal operation, it could have a little bit of a resistance. An example is if you have a 10 ohm NTC thermistor, and 10 ohm when it's cold, and when it heats up, it becomes 1 ohm. But in a 1 ohm resistor, if you have, let's say, a 1 amp RMS current or something in that order, you could still have a watt of dissipation. So it is good to be able to eliminate the thermistor to get that small efficiency improvement. And again, the other good thing is that because your inrush current is very small and you don't have to have these slow blow fuses to allow large current initially, you can use a fast blow fuse, and this leads to better fire safety as well, which is also important in this application. And the other thing I wanted to point out regarding the buck topology is about this paper by Bobelier, which looks at failure analysis for various power supply equipment used in the LHC experiments. And you see an interesting pattern here. Quite a large percentage of the failures are because of the PFC, and it is also surmised that it is because of the high inrush current, again stressing the devices beyond their required or specified temperature range, and this over a long period of time can, if you have repeated turn on and turn off, that is, can cause reliability issues. So this again is circumvented, this problem of inrush current based failures is circumvented by using buck topology, giving you a very high reliability power supply. This is also a reminder of a little bit of engineering philosophy, that successful engineering is all about understanding how things break or fail. And of course, once we understand how things break, we can look into how to not make it break.
What is the x-axis here in the plot? PL.
So each one of these is, let's say, a particular make of power supply. So there is no numerical quantity on the x-axis here. So it just shows that this make had these few different failure modes or modules failing. And you can say that in 3 different makes, it was the PFC, in this case, PFC boost, that had the highest number of failures.
And within PFC, was it the switch or?
Yeah, it is typically a shorted main MOSFET. Again, I cannot be very sure, but it is likely that it is because of the high inrush currents, and especially if the application involved several restarts.
Okay. Thank you. Please go ahead.
Any more questions at this point?
Right now, no, Dr. Lalit. Please go ahead. I'll interrupt you if there are any in the chat.
Okay, yeah. Okay, as we discussed just a few minutes back, the question came up about the choice of the DC link voltage. And for any value that you choose between 0 to 400, of course, there is a trade-off. And first of all, I explained in the previous slides why we do not want to use the boost topology. So if you do not want to use the boost topology, the DC link voltage cannot be higher than the peak of the AC voltage. So obviously, all of this was ruled out. And then you have this, let's say, 100 to 325 volts, where you can operate a buck topology. But as we mentioned, there is large crossover distortion. The blanking period can be very short, and you get hardly any power factor improvement. So this again has to be ruled out. And then you have this kind of sweet spot in 36 to 100 volts, where it is possible to operate a buck topology in a satisfactory manner. And if you go much lower in the voltage, the MOSFET duty cycle, average duty cycle, so to say, is so low that you get very high peak currents and very poor efficiency. And in our case, the best kind of solution, taking into account all these trade-offs, was about 36 to 72 volts, and let's say 48 volt, which is kind of a standard value, is what we chose as the nominal value. So there is this caveat that should be brought up whenever using PFC buck topology. Apart from the crossover distortion, which is an issue, you have this issue of the shaping of the current, and which is actually in a way controlled by the slope compensation. So when I say slope compensation, I'm talking of using a current mode control scheme. So in this current mode control, as some of you might be aware, you need slope compensation to take care of or to avoid what are called subharmonic instabilities. But when you add a slope compensation, there is a choice regarding what should be the extent of the slope compensation, here expressed in terms of a KS factor. And you can think of it as low value of Ks is low slope compensation and high value of Ks is high slope compensation. And if you choose a very low slope compensation, you get this red waveform, the shape of the current that is. And you can imagine this as the current waveform growing horns here, two horns growing, looks like a cat almost, yeah. And you don't like this. Why? Because you have this high frequency component in this current, which again is something that the utility company would not like, and you want a more nice and rounded current with low frequency, 100 hertz or rather 50 hertz on the AC side. So you can go on increasing the Ks value or the slope compensation, and you will see that if you have too much slope compensation, you end up with a spiky current, and it can go higher and higher, and you will end up being very close to not having any power factor correction. And this is also something you need to avoid. So there is some kind of an optimization again here, which again is something that in theory you can arrive at the Ks value that is optimal, but in practice there are a number of different factors, especially relating to noise in the inner control loop, which play a bigger role than all the modeling that you do, circuit modeling that you do, and you sometimes have to do a trial and error kind of approach to arrive at the optimal value of slope compensation. By the way, this figure is again taken from this nice paper by Huber et al. In 2009, again on the PFC buck topology and the current shapes that you get in different conditions. So as far as our implementation of the PFC buck is concerned, this is a simplified schematic of the whole PFC buck. As I said before, people have done this before. There was the paper in 1992, the first one, and there is this very good work in 2009. So what is different in our way of implementing it? The main difference I would say is in making this topology radiation tolerant. So what are the different design considerations you should take in a PFC buck so that you can now take this AC-DC converter and use it in radiation exposed applications? And I mentioned some of the points before this, and in the coming slides there will be more of the design aspects you need to take into consideration for making this standard PFC buck topology radiation tolerant. And here again, this article by Texas Instruments is a very good reference because it goes through the design of different parts of the converter in detail, including all the design equations. I highly recommend this article for if you need to look into some of the details. Just to just as an overview of what we see here, you need some kind of filtering because you have a buck topology, which means you have a switching current at the input side, and hence you need a good amount of noise filtering, both common mode and differential mode. And this again is a very standard design. And then of course you have the rectifier, which is a standard diode bridge rectifier, and then you have this buck converter sitting here, where you sense the MOSFET current and use it for the inner current control loop. One small issue here is that the ground of the controller, that is the ground with respect to which you're also measuring your current, is actually different from the ground of the output side, where you measure your 48 volts. Because you have all these devices in between. So you have to use some kind of a translator to take this sensed voltage, output voltage, and translate it to the new ground so that that can be used by the control chip. This again is well known, nothing new. You will find it in the literature that I mentioned before. But this needs to be taken into consideration because otherwise we will have smoke on the table. And this PWM chip is a COTS chip. It's the standard TL2843. This particular one passed many of the radiation tests that we did on it, up to total ionizing dose of about 500 gray actually for just this chip. And then the compensation used is a standard type 2 compensation, which is very common for current mode control. This is a picture of the...
There's one question on your choice of control implementation. Why analog and not digital?
Yes, that's again a very nice, good question. Again, radiation exposed applications, sometimes it can be hard to find a controller chip that passes all the tests. Essentially, the problem here is one of integration. So you have so many different things inside many of the digital controllers, microcontrollers, that it is very difficult to find a chip in which all of the sections pass the radiation test. The ADC should pass the radiation test, the PWM should pass the radiation test, the processor itself should pass the radiation test, and so on, the oscillator and everything. So considering the level of integration in digital chips, unless the chip itself is designed with radiation hardness in mind, it is hard to find chips that pass all the radiation tests for all different parts of the chip. So just from that point of view, from the radiation tolerance point of view, it is good to have a simple control circuit, something that doesn't have a high level of integration. And these analog chips have been around for a long time, and it's not a very difficult control application in this case. So it's possible to implement it with analog, and that is why we chose this approach.
Okay. Thank you, Dr. Lalit. Please go ahead.
Yeah. So yeah, this is a picture of the PFC buck, our prototype, lab prototype. And this is the diode bridge on the input side, the EMI filter, the main MOSFET, and the freewheeling diode, the PWM controller, output inductor, and the output capacitors, which are quite large compared to a boost topology actually. So that is another difference with respect to the boost topology. You actually need larger capacitors on the output side, excuse me. And all this space here is something we will be using for the DC-DC stage, which does the 48 volt to 12 volt conversion. And this is the test result under radiation for the 800 volt MOSFET that we chose because it passed all the radiation tests. This is an Infineon part, an 800 volt device. And what you see here is essentially the ID versus VGS. So essentially you are trying to see at what gate source voltage is the device turning on. And let's say you take a MOSFET which is not irradiated. So these solid lines here show a MOSFET that is not irradiated. And that has a threshold voltage of, let's say, 3.2 volts at which it starts conducting. But if you irradiate the MOSFET, its threshold voltage starts drifting to the left. That is, the threshold voltage is decreasing, even in the absence of any gate voltage. So even if the MOSFET is just off all the time, its threshold voltage would still drift by a little bit. And in fact, if you have some average gate bias applied to the MOSFET, that is, it is an operational MOSFET, its threshold voltage can drift even more. And this shows results for up to 250 grays of total ionizing dose. If you go up to 500 grays, you see that the threshold voltage has actually become negative. And basically, if your threshold voltage at the gate of the MOSFET is less than 0, the MOSFET is uncontrollable. It's always on. And so you cannot any longer use this MOSFET. Another way of showing this same thing is to look at the threshold voltage versus total ionizing dose. And Okay, to give an idea of what this total ionizing dose means, in the planned LHC, high luminosity LHC operation, in areas that are most radiation exposed, we expect something like 25 grays of accumulated dose. So this total ionizing dose is like a quantity that is accumulating or integrating over time. So over 1 year, you accumulate about 25 grays of total ionizing dose. So if 1 year is 25 grays, let's say 300 gray is 300 divided by 25, which is about 12 years of operation. So this is about 12 years of LHC operation. This is about 20 years of LHC operation. So in some sense, you are saying you kept the power supply on for this many years, and at this point, the MOSFET has failed, and you cannot any longer control it. In fact, the failure would happen when the threshold is close to 0. So basically, this pink region here is forbidden region, and you can see that if you reduce the gate bias, so these are the 3 gate bias voltages. If you reduce the average gate bias, you are able to let's say reduce the amount of drift that occurs in the threshold voltage. So do not go for a normal 12 volt, 15 volt kind of a gate drive. Keep it to a maximum of 10 volts or so. And when you have 10 volts with a PWM of, let's say, an average duty of 30% or 40%, whatever it is, the average gate bias would be, let's say, 2 to 4 volts. And then you are reasonably okay in terms of the threshold drift not being too much. So this is one key design measure where you should choose the gate drive voltage correctly, so that over the entire lifetime of the MOSFET, the threshold voltage doesn't drift as much as to make the MOSFET uncontrollable. And there is a second issue apart from the threshold voltage drift. The other problem in power MOSFETs is what is called single event burnout. So while the previous issue was that of a slow wear out kind of failure, this one is a sudden catastrophic failure where one event happens and suddenly the MOSFET is shorted. And this again, you have to test for, again, the same MOSFET that I talked about before, tested with a defined amount of drain source voltage applied to it and seeing if it fails. And you do it for a number of devices to establish what is the probability of failure of the device. So the single event burnout cross section is kind of proportional to the probability of a single event burnout happening in the MOSFET. And what you see is that below about 540 volts or so, there are no failures. And in our design, the maximum VDS seen by the MOSFET is about 375 volts. If you have high line, let's say 265 volts of AC RMS voltage, even in that case, it would be a peak voltage of 375 volts. And so using an 800 volt MOSFET, you have something like 50% VDS derating, and this ensures that there are no single event burnout events in the MOSFET. At this point, do I have any more questions? Okay, if not, I will move ahead.
There are couple of questions.
Okay,
Dr.
yeah,
Lalit.
I can
Maybe
take
we'll just, yeah. So one is, okay, let me just, Nachiketa, please go ahead. I think you have a lot. Please go ahead. Okay. Anyway, he asks, your prototype shows electrolytic capacitors. So according to my knowledge, they're infamous for rapid degradation at very high temperature, even the polymer electrolytic ones. So considering you're targeting high lifetime, that is aerospace, can you please comment on the choice of output capacitors?
Yeah, that is again a very valid point. And the only way to get around this problem is, first of all, to use very good quality capacitors. So nothing other than the best makers, let's say Panasonic, Nichicon, Rubicon, all these well-known brands with 105 degrees Celsius rated capacitors and never 85 degrees Celsius rated capacitors. So that is one. And the second would be the amount of derating you have in terms of temperature of operation and voltage of operation. So we use 100-volt capacitors, whereas the nominal operation is at 48 volts. So there is again a big derating factor there. And again, in terms of temperature, with respect to the 105 rating of 105 degrees Celsius rating of the capacitors, if we operate at let's say 45, 50 volts, 50 degrees Celsius or so, again we have a big derating there. So these are the only ways we can get around the problem of the reliability or the lack thereof in electrolytic capacitors.
Yeah, one follow-up question from Nachiketa. Can you please comment on the non-synchronous design of the buck converter? One may expect an improvement in efficiency for a synchronous design. So any comments on that?
So if you are talking about the synchronization of the PWM with respect to the line cycle, is that what he's referring to?
Nachiketa, can you please clarify what exactly you mean?
Can you please go back, Dr. Lalit, go back to your schematic? Yeah, here you are using this, I'm saying DF, right? Instead of DF, you can use one more MOSFET there, right?
Yes. Okay, yeah. Okay, so you're talking of using synchronous rectification, not PWM synchronization.
Yes, sir.
Yes. Yeah. In fact, that is also something you could do. It's just something we chose not to do because, again, you have to add the gate drive and all that for that. And synchronous rectification is something that becomes more important in, let's say, higher current applications, whereas here, just a couple of amps or so, it is okay to not use synchronous rectification and add complexity to the design. So, but yes, the efficiency will go up if we use that.
Sir, did you compare how much efficiency gain you will make? Because at least in my understanding, for most of the time, this diode will conduct, right, sir? Because the input voltage is very high.
You're right. Yes.
And most of the time the diode will conduct. So if I am able to reduce that voltage drop, I may have a quite bit of efficiency gain. So I may be wrong.
No, this is absolutely correct. So it's about, are we prepared to lose that much energy or not, and add the extra complexity to the design? Because again, when you add the gate driver, you have to ensure that the gate driver is also radiation qualified for both low side and high side driving. So that again becomes an issue, but I agree that in principle the efficiency will increase. So to give some numbers to this, let's say you had about 10 watts of dissipation in the whole system, slightly more I would say in our implementation, because I will come to why efficiency is kind of a challenge in radiation tolerant applications. But if you have 10 watts of dissipation, something like 2 watts is in the diode. So it is 20%. It's big, but if you can live with it, you just live with it instead of adding complexity to the design. So if that answers your question.
Okay. And Dr. Lalit, I had a follow-up question to your previous answer. You had said that you are increasing the you are sort of over designing the output capacitor bank, if I have understood it correctly.
Yes.
So there is one more way that what we can do is we can use an active circuit, an additional active circuit, and we can replace this output capacitor with sort of a active circuit and a very small value of, let us say, film capacitor. So those
do you have some suggested reference for that?
Yeah, so those circuits are termed as active hour decoupling circuits.
Okay, yeah. So essentially, you use a smaller capacitor and some electronics with it to make it look like a bigger capacitor.
Yes, and that smaller capacitor can be of film type, so that you get extra reliability. Did you consider these circuits? I am just wondering.
We have not. In fact, I would say in terms of the PFC stage, our focus was on trying to make it as simple as possible, because we also have, let's say, volume constraints here. We have 2 more channels of DC-DC in the same card. And I agree that if you make the capacitor smaller, you add up, let's say you have extra volume to play with. So maybe that could help. I'll take a look at it. Yeah, but this is something we have not considered at this point, just in the spirit of simple design.
Okay, makes sense. Thank you.
Thank you, Nachiketa. Dr. Akif, can you please unmute yourself and go ahead?
Yeah, Dr. Lalit, can you hear me?
Yes, please go ahead.
Yeah. So my question was regarding your AC/DC stage, the PFC stage. So why you didn't go for like more fancy topologies like a totem pole, bridgeless AC/DC stage to get better efficiency?
So it's again the same issue of complexity. Like if, let's say, you have something like, I don't know, 300, 500, 1 kilowatt, 300 watts, 500 watts, or 1 kilowatt, or even higher, then it makes sense to go to those kinds of topologies with larger number of devices. In a 100-watt kind of an application, it many a time becomes overkill to go for more and more complexity in the design, just from a cost point of view.
Okay, thank you very much.
Yeah, and one more question he had put in the chat was, I don't think any wide band gap devices were used, right? Silicon.
No, this is all silicon. Yeah.
Oh. Please go ahead, Dr. Lalit.
Because you brought the topic of wide band gap devices, this is again something interesting. With respect to radiation hardness, it is actually let's say more tolerant to ionizing radiation than silicon, many of the wide band gap devices. But what is not still very clear with respect to wide band gap devices is the single event burnout, the probability of these SEB events. And some people suggest that you might have to derate the VDS to even 10% to be sure of safety with respect to SEB. So already 50% derating is a lot, which you use in silicon. And if you have to use 10%, which means like if the actual requirement here is 400 volts, you need something like, I don't know, 4 kilovolt device. And it's just again overkill. So I'm not sure these results hold across all the different varieties of wide bandgap devices that are coming these days, because every week you have these new devices from a new company and so on. So it's still an evolving area, which I would say is not well understood in terms of radiation tolerance.
Yes. Please go ahead, Doctor.
Yeah. Okay. Where was I? Yeah. Moving on to the results. The input voltage is this sinusoid here, and the input current is not as good as you would see in a boost topology, but still much higher power factor than you would have without power factor correction. The measured power factor is actually better than 90%, and both in simulation and experiment, that is. And this is the output voltage that you see. In this case, we are operating with 230 volt AC input, 48 volt output. So the ripple is about 5% at 100 hertz, which is acceptable because you have a DC-DC stage following the AC-DC stage, which will further tighten the voltage ripple specification to be whatever is the specification for the load, typically 100 millivolts or even 50 millivolts kind of peak-to-peak ripple. And these are results for dynamic loading. This question also came up some time back in the early slides. So we changed the load here to from half an amp to 1 amp. So you're talking of at 48 volts, about 48 watt to 96 watt, let's say 50 watt to 100 watt, and with a slew rate of 5 amp per millisecond. Note that this is not a very sudden change, because most of the dynamic loading is in fact handled by the DC-DC stage, as I mentioned before. And the DC link voltage just has to be maintained within the limits of the DC-DC input. which is 36 to 72 volts. So this is well within regulation. And as I mentioned before, the control loop bandwidth is about 10 hertz for the AC/DC stage. And this is power factor versus load. Again, if for higher loads, you have better power factor. And it is at higher loads that you are more worried about power factor. And in terms of efficiency, initially the published results in PSIM, we had about 85% or so, which was not very good, but with all the deratings that we had for MOSFET VDS voltage, VGS voltage, it was something that was a result of that, I guess. And we had to do various maneuvers or modifications in the design to improve the efficiency, and the present prototype is almost 90% efficient. So we can discuss a bit about the efficiency improvement measures. The main one I would say is moving from a COTS inductor to a custom inductor. This one was just a single winding, in the sense one large copper wire, large area of cross section, whereas you split that large area cross section into 4 parallel windings of smaller area of cross section, so that let's say the skin effect issues are lesser. And with this custom inductor, we got a slightly higher inductance as well, within pretty much the similar volume. And if you look at the resistance versus frequency, we are not very far away from the COTS one, but the main thing was that because of higher inductance, the peak currents went down and the efficiency went up by quite a lot. So the message from that experience would be on magnetics design. It doesn't matter what your topology is, what kind of devices you use, how good your control is. If the magnetic components are not designed well, none of the other design aspects can rescue the power supply design. And this is something that comes up again and again in different power supply designs, the importance of the magnetic components and designing them properly, and which is why custom design makes sense for magnetic components in many applications. This is a snippet from a classic by Marty Brown, which talks about designing the magnetic elements first and then moving on to anything else in the power supply, like accompanying power circuits and low-level control circuitry. And to quote Robert Mamano, who is like a guru in power supply design from Texas Instruments, he's a TI fellow, probably retired now, but he mentioned in one of his books or articles that the design of magnetic components is the easiest place to jeopardize a power supply design project. And you can do everything else right, and still your power supply would be crappy and lossy. Moving back to other efficiency improvement measures, we tweaked with the gate drive to have faster turn on and turn off of the MOSFET to reduce the switching losses. We were able to eliminate the snubber in the MOSFET because the ringing was actually not at all there in the MOSFET VDS. So we were unnecessarily using a snubber, or maybe using too much snubbing, which is something which is counterintuitive, because you want ideally a snubber to protect the MOSFET. But in this case, considering the amount of ringing that we had over-designed it. And so even eliminating the snubber was possible in the design, which also helped increase the efficiency a little bit. And the other one would be changing the DF, that is the freewheeling diode, from silicon to silicon carbide. This is also a change that gave us a slightly lower forward voltage, and of course no reverse recovery, at least theoretically speaking. In practice, even silicon carbide Schottky diodes have something similar to a reverse recovery phenomenon, which is because of the junction capacitance of these devices. So even though you expect that when the diode goes from on to off, it should be without any reverse current conduction, because of this parasitic capacitance, you have a little bit of reverse current conduction, but still these devices would do way better than any ultra fast silicon diodes. And with all these improvements, we got, let's say, about 4 to 5% efficiency improvement, which doesn't look like a lot, but that is almost a 30% reduction in losses. And because of that, the inductor as well as MOSFET run 35 degrees cooler, which is a huge improvement in terms of the reliability of the system. So to conclude, we saw the design of a 100-watt radiation-tolerant PFC buck converter using COTS components. And with a standard AC input and 48-volt DC output, you are able to get both good power factor as well as reasonably good output voltage ripple that can be fixed by the DC-DC stage. You get reasonably good efficiency as well as tolerance to radiation up to 300 grays. So this design is validated based on simulation, lab experiments, as well as component level radiation tests. We are yet to do system level radiation tests, that is the entire board being irradiated. And this is something that is planned in the coming months, both in terms of gamma ray radiations and proton beam radiations. And as I said before, the project is available on Open Hardware repository with all the files, design files freely. So this is again the relevant publication in PSIM, which goes into the details of the design. And in a few days, we also plan to upload the detailed design report to this link here. It's not yet up there, but soon we will have that as well to make the design as open as possible. Thank you for your time today, and I can take more questions if there are any.
Thank you. Thank you, Dr. Lalit. Excellent presentation. Dr. Sudarshan, please unmute yourself and go ahead with your question. Please go ahead.
Oh, thank you, Janmejaya. So it's always a very nice thing to listen to Dr. Lalit. One question that I had in my mind is, as a thumb rule, can we tell, can we come up with a factor which relates derating factor versus lifetime degradation or lifetime improvement of a device in radiation tolerant environment?
That's an interesting question. Maybe it is possible to do this at a device level. I'm not sure you could do this at the full system level. Because
not at the system level, but at least classes of devices. For example, it could be capacitors, or it could be resistors, or it could be semiconductors.
I think there are some thumb rules on this based more on practice rather than any modeling. I would say that the theory on this aspect is still a bit limited, chiefly because the people with the radiation expertise do not have as much expertise on the electronic side, and the people with the electronics expertise do not have as much expertise on the radiation side. Whereas the question that you asked is actually at the border. So one needs to know well both aspects to come up with a theory that gives you a prediction of this derating versus life. So what has ended up happening, as is the case with many interdisciplinary things, is that you come up with thumb rules based on practice. And this is in fact a very good opportunity for research if people want to try it. But I don't know of any first principles based approach to this derating. It's all practice, trial and error based.
Okay.
Okay, thank you, Dr. Sudarshan. Nachiketa, please go ahead, unmute yourself and go ahead.
Thank you. I had a question, Dr. Lalit. In a slide, you have shown that the threshold voltage of the MOSFET drops, and when it goes below 0, you are saying that it is not possible to control the MOSFET, to which I agree. So I was wondering if it is possible to use the negative voltage to control the MOSFET in that region.
Yeah, that's again something that is a very good idea. The reason why one would not want to do it, there are actually two reasons. One is, first of all, when you turn on the power supply was sitting completely, let's say, unpowered. There was no electrons flowing in the power supply, and suddenly you turn it on. And at that moment, you need the negative voltage to be available to keep the MOSFET off. Otherwise, it's a normally on MOSFET. So because of this problem of basically, again, you have to have some kind of sequencing of power to different parts of the power supply, where you have to first generate a negative voltage applied to the MOSFET and then apply the VDS across the MOSFET. So it again adds quite a lot of complexity to the design. This is one aspect about the MOSFET being on by default when you turn on the power supply. The second problem is regarding single event gate rupture, which is also kind of a failure mode in radiation for MOSFETs. And it is known that with negative gate bias, the probability of these SEGR, single event gate rupture events, goes up. So that again is a deterrent for going to negative voltage being applied at the gate.
Okay, okay. Thank you, Dr. Lalit. Thank you for your presentation and thank you for answering the questions.
Thank you.
Thank you, everyone. Dr. Lalit, I had one question regarding the MOSFET. If you look at the chat, do you have the MOSFET datasheet at hand? I have put it in the chat as well. You can quickly open it.
Let me see. I probably don't.
Yeah, you can download it from the chat.
I don't know, maybe it's easier to just search for it. IPA.
Yeah, IPA 80R2. Yeah, I just.
Yes.
Yeah. What I wanted to know was, how did you, let's say, typically you'll have your voltage rating and current rating by which you land on few devices. Then when you come to the data sheet, what specific things do we look for? Maybe you can share the data sheet and then.
Are you able to see the data sheet?
No.
No?
Maybe
You are seeing the slides, I guess.
Yeah.
Okay. Just a minute.
Yeah.
New share.
And that video.
Now?
Yes.
Okay, yeah.
Yeah. So my question was, when we land on the data sheet, what do we look for? Because there are obviously lots of plots. So we know the application, we know the specification. Now, once we come here, what do we look for? Because obviously at this voltage range, there'll be a couple of MOSFET.
Yeah. So is your question with regard to normal applications or radiation tolerant applications?
Normal.
With normal applications, it's just about, from the topology, let's say from the ideal operation of the topology, you have some voltage and current waveforms. So based on that, you have some specification on the peak voltage that the MOSFET needs to block, and let's say the RMS current and the peak current that the MOSFET needs to conduct. And that is a good starting point. Although here there is a caveat. I would say in most cases, I would not look at the current rating of any semiconductor device because they are typically coated for very good cooling conditions where you have some large heat sink or something like that, something that is controlling the temperature of the MOSFET very nicely. So the thumb rule for me is to look at the loss mechanism, which in most cases is mostly the conduction loss. Could be a lot of switching loss as well, but a starting point is to just look at the RDS on. And for the RMS current that you expect through the device, you have an I square R loss. And based on the power dissipation and the kind of heat sink you are using, the thermal analysis, you can get an estimate on the junction temperature of the MOSFET and see that it is safe, let's say below 80 degrees or 100 degrees.
Okay. And also in the paper you mentioned you acknowledged few people's help as well. So you selected bunch of active switch MOSFETs and then they were radiation tested, or how did the process happen?
Yeah, so at CERN we have, let's say, design groups consisting of electronics engineers who design all these different circuits and PCBs. And then we have groups that have, let's say, more expertise on the radiation physics side of things and radiation effects on electronic devices, these kinds of things. So let's say these are radiation physicists or radiation engineers. And typically we work together in terms of, let's say, the electronics design engineer would come up with some kind of a topology and some kind of schematic, and then say, okay, these are the devices that I'm looking at, and you come up with a few different options of part-to-part replaceable devices and give them to the other team, radiation experts, and ask them for their inputs on, do they see any red flags, or what are the drifts in the various parameters of these devices that they expect. And they know how to carry out the radiation tests for these devices. It's like a service we use. So they would look at everything that they can from the theory, from the actual experimental irradiation of these devices, and then come up with a recommendation for us that among these devices, this one is the best. Sometimes they would say that none of these devices are good. Take this fifth device that somebody else is using, and this does well for these kinds of specs. So it's something like that. So it's a very collaborative work.
Yeah, this also is a very unique application, because if you just take aerospace application, you don't have a AC source at all. You just have all DC sources. But because of your
you do have 400 volts, not 400 volts, 400 hertz AC in aerospace. So it is there, but I agree that in many ways this is unique in terms of the radiation tolerant requirements. But again, I would also say that because we live in this small biosphere shell of, I don't know, 8 kilometers around the Earth, we say this, but if you go deep inside Earth to do high energy physics experiments, or you go deep in space to do, I don't know, satellites and spacecrafts, everywhere there is radiation. So yeah, it kind of looks like radiation tolerance is unique, but actually not having radiation is unique. I mean, we are in a safe setting.
Yeah. Very good. Thank you, Dr. Lalit. Excellent presentation. Thank you for your time.
Thank you.
Thank you for publishing as well, because sometimes many of the novelties, they're not published in companies or in research centers also.
Yeah, I mean, different people have different philosophies of how they go about hiding or disseminating their design. At CERN, the philosophy has always been of having open designs, maybe because it's publicly funded, but I can see lots of applications where if you are doing business, if your income depends on your design, then somebody can choose to not have the designs open. So yeah, I mean, there are all kinds of people with all kinds of requirements. We happen to be lucky enough to be able to share our designs.
Yeah. Thank you very much, because it's incredibly, during this time, very difficult to get practicing engineers to give talks. And thank you for sharing your expertise with us. And we hope to see more publications from you in the future.
Sure. Thank you so much to all of you.
Yeah. Thank you, everyone. Yeah. Have a good day. Thanks.
Bye.